Hello everyone, my name is Mark. Today we're going to talk about how to solve partial differential equations, PDE, through the method of separation of variables. Before we actually go ahead and solve any PDEs, I want to do some review with you so that you have a basic understanding and the techniques of how to solve PDEs. So let's get started. So the first topic I want to talk about is characteristic equations and integrating factors. So these are the top, these are all under the category of linear differential equations. So characteristic equation and integrating factor. I'm gonna draw some blue boxes to indicate that this is a topic. So just like that. So let's talk about characteristic equation first. So this is going to be a very simple one, and that is x double prime plus lambda x equals to 0, and you might have know that this equation has three cases, and then the first case is lambda greater than 0, second case is lambda equals to 0, third case is lambda equals to 0. Smaller than 0 equal is the second case. So the first case is if lambda is greater than 0, then our characteristic equation becomes r squared plus lambda equals to 0. Why r squared plus lambda equals to 0, you ask? And that is because this x has second derivative, so second derivative, second order, no derivative, no order. So our root becomes r equals to positive or negative square root of lambda I, and then our solution becomes x equals to c1 cosine of lambda t plus c2 sine square root of lambda t. Why no I, you ask? And that is because our arbitrary constant c1 and c2, especially the c2, has already absorbed this imaginary number. Okay, second case, if lambda equals to 0, no r actually, this becomes very easy differential equation to solve, and that is x double prime equals to 0, and that leads us to x prime equals to a, and then lead us to x equals to a t plus b. You can use c1 and c2, but this is kind of a special case, so I'll just use a and b. So if lambda is smaller than 0, our last case, r squared minus lambda equals to 0, and then similar to case 1, r equals to positive or negative lambda, no I. And then x equals to c1 e square root of lambda t plus c2 e to the negative square root of lambda t. So this is what you do know for about characteristic equations. And then we're going to talk about another differential equation, and that is y prime plus lambda y equals to 0. I'm just using a different variable here. So we're going to solve this first order linear differential equation through the method of integrating factor. So to solve integrating factor, we need to identify our q and the p. So the p of x equals to lambda, and q of x equals to 0. And then what we need to do is to find our integrating factor, and that is I of x equals to e to the infinite integral of px dt, px d, actually not, let's not use x, like t, because we used t above. So pt dt, and that will give us e to the infinite series of lambda dt, and that gives us e to the lambda t. So our solutions is in the form of so y equals to 1 over I t, big bracket of integrating of qt and I t dt plus an arbitrary constant of c1, and that will lead us to, actually let's analyze this in a big expression a little bit, because we know that the qt is 0, so this whole term becomes 0. So our y would become to 1 over I t, and then this integration of 0, which is I'll just use c2 plus c1, and then that will give us and then I'll just let c2 equals to c1 equals to c3, so the answer is c3 of e to the lambda t. So the answer is c3 e to the negative lambda t. All right, the next thing I want to talk about is Fourier series. So let me just go ahead and pop a bunch of equations down, and I will go through them later one by one. And then just like so, we are good. All right. So the idea behind the Fourier series is very similar to the idea behind Taylor series. So Taylor series, we're trying to model a bunch of analytical functions using a bunch of sum of other functions, let's say polynomials. In the Fourier series case, we're trying to model periodic function with bunch of which a bunch of means a sum of cosine and sine functions, because cosine and sines, they are linearly independent, so that's why Fourier series can work. So this is just a brief description about Fourier series. So the first Fourier series, which is right here, it's not a general Fourier series, but this is a common Fourier series that you'll often encounter. So what's interesting about this one is that so the t is in the domain of negative pi to pi, with L, which I interpret as length of pi, and a period of 2 pi. So L is always half of p. So the Fourier series is 1/2 a0 plus infinite series of an times cosine nt, and then bn times sines nt, where an equals to 1 over pi, integral from negative pi to pi, so that's the interval of t, of ft cosine nt dt, and then bn is 1 over pi. This is the same thing as the an with modification from cosine to sine. Okay. And let's look at the general Fourier series. So what's interesting about this one, important things are labeled in pink because it's quite contrasty. I like that. So instead of being constraining this weird length of negative pi to pi, we now have negative L to L, where L just equals to L. So we're no longer constrained that by in that weird section. What you would notice is that the Fourier series changes from, instead of cosine of nt, now we have cosine m pi t over L, and then sine m pi t over L. Our integral changes a little bit. Instead of pi, now we have L, and then this is the same thing as we saw up here. An interesting observation is that if you replace all of these L with pi, you will get the same thing as as this common Fourier series that we just talked about. But if you know, but it's still kind of awkward that we are constrained in this symmetrical domain. So how we can get rid of that symmetry, and that's what the third Fourier series comes in. So what's interesting about this one is the domain is from 0 to 2L. So what's changed is just the interval of integration. So from negative L to L, now from 0 to 2L. Now it's Fourier cosine series and Fourier sine series. So what's interesting about these two is that if a function is an odd function, so that means this graph of the function is symmetrical with respect to the y-axis. For example, y equals to 2t, not 2t, y equals to t over t to the second power, so t squared, or a cosine t. So these will fall into the even function category. And those functions Fourier series can be simplified down to a0 over 2 plus infinite series of an cosine n pi t over L. So it's basically that the sine part is canceled out because of the, if you do the integration, you will find that for all of the even functions, the b term will always get canceled out. So no b term, only a term, and then the an is the same thing as before. And then for the sine series is the opposite. The functions are odd functions. Has to be odd functions. That means the graph of the function is symmetrical with respect to the origin instead of the y-axis. So functions like sine of t or y equals to t or y equals to t to the cubic, those fall into this category. And then for your sine series, instead of instead of the b terms gets eradicated or gets eliminated, the a terms gets canceled out. So what's left is only b. So Fourier series is infinite series of bn times sine n pi t, where bn is same as before. So this is all the things that you need to know about. So we started with characteristic equations and integrating factors, and then Fourier series. So Fourier series, what's important is all of our solutions for our partial differential equations will be in the form of Fourier series, one way or the other. So that's it. I'll see you in the next video.